Okay. Philip Engel from University of Georgia. He's going to teach us doing that conjunction.
Yeah, thank you for the invitation, introduction. So if thought first we could review what are the sort of relevant objects of interest. We'll start with like a little bit more algebraic geometry perspective, and then we'll maybe see some symplectic geometry at the end. So let me give the following definition. So complex surface is a manifold with charts to C2 and holomorphic transition functions. So for a simple example, we might have the complex plane itself, which just maps to C2 by the identity. It has one chart. Maybe for another example, we could take C2 mod Z2, where this Z2 acts on C2 by translation. So this would be an example of a complex surface, because if I translate C2 by a pair of integers, then that would be a holomorphic transition function. Maybe another example might be the vanishing locus of, so let's consider all of the x, y, z in C3 such that z equals x cubed plus y squared, something like this. So this is an example. So this is a hypersurface in three-dimensional complex space. So it's going to have two complex dimensions instead of three. And in this case, there are local charts to C2. So you can in fact construct globally a chart to C2, which is to map this to xy. Since z is uniquely determined by xy, this is a homeomorphism, and that defines an isomorphism with C2, let's say. And I want to sort of give a name to these types of objects where I take the vanishing locus of some polynomial equations. So I'll write this as the vanishing locus of the polynomial x cubed plus y squared minus z. Okay, so that's just the notation for the vanishing locus of this polynomial equation in C3. Great. Give an example. So what if I take the vanishing locus instead of, say, x squared plus y squared minus z squared? So this is also contained in C3. So maybe for visualization purposes, we can think about the solutions of this equation over the real numbers instead of the complex numbers, right? So let's draw the picture. So a picture in R3 instead of C3, well, we get some sort of circular cone like this. This is the vanishing locus of this polynomial, right? It says that at height z, we have a circle of radius c, right? And this is sort of obviously not, this isn't a real surface because of this point here. So the issue with this point is that there's really no neighborhood, no matter how small of this point, that we can take where this has the structure of a manifold. You know, this is never homeomorphic to a disk, right? Okay, so that is an example of what we call a singularity. So a singularity of a vanishing locus of polynomials will mess up the structure. It won't be a complex surface. So you can take that as the definition of a singularity, for instance. It's like a point on the vanishing locus of some polynomials where it doesn't have the structure of a manifold. And in fact, let's give a name to this singularity. This is the simplest sort of singularity of surfaces, called the A1 singularity. So this is the sort of simplest surface singularity. And then I do want to give one other example, sort of just along these lines, very similar. Here. What if similarly, I could take like the vanishing locus of x cubed plus y cubed minus z cubed contained in C3. And instead here, we have, it's some sort of cone-like shape, right? Because this is a homogeneous equation, right? So this is, every term is degree 3. And so if we scale a solution to this equals 0, we would get another solution to this equals 0. You know, if we have a solution, then the whole line containing that point through the origin is solutions. So this is okay. All right. So I want to talk a little bit about resolution of singularities. So resolution of singularities is a procedure. So this is some sort of procedure to replace a singular surface complex, which we would sort of call a smooth complex surface. Okay, so what is this procedure? So in dimension 2, this is a pretty algorithmic thing. What you do is, if you have some points of your surface, and this produces a new space. Maybe it still has some singular points, but then you blow those up, and this eventually terminates, and you get a complex surface. You have to do something called blowing up the singularity. What is this? I'm not going to define it carefully, but it's sort of some sort of way to replace a point in a complex manifold with all of the tangent directions to the point. So to sort of replace the tangent directions sorry, replace a point with its sort of tangent directions. Okay, so maybe for a couple simple examples of blowing up, where did I? The sort of simplest example is if you have a complex surface. So you already have some smooth thing. Like for instance, we could take C2 itself, right? And then we take the 0. Then there's this procedure called the blowup. Let's call this map pi. So we'll notate it as the blowup at 0, 0 of C2. And so sort of Umu drew this picture already, where this point is placed with some complex curve E. E here is contained in the blowup and maps by this map pi to the point 0, 0. And what is E? E sort of records all directions through this point, right? So the set of directions through the origin in C2 is identified with CP. So this is just we've replaced point with a line. Okay. So now I want to do this same thing, but what if I blow this point of this singular? Yeah. Sure.
Situation like we've been doing for getting the storage model, for example, right? So because that operation doesn't do anything outside of the, it just replaces the point of E, the rest is exactly the same. So you can implant that to different places.
So yeah, maybe I should write that.
Just because I think maybe it's a good place for sex up respect.
So if we blow up and we sort of subtract out this exceptional curve, this holomorphic map pi restricted to that gives an isomorphism to C2 minus the origin. So this is just a general procedure be done to a surface, produces a new complex surface, which is, yeah, isomorphic away from the point, but replaces the point with all of its tangent directions. It's not that crazy to write down. Maybe I should just take the opportunity to write it down. So like coordinates are like x, y, C2. That's x, y. So the coordinates on the blow are something like x mu, where mu is the slope of the line. So is the slope, like y over x, is that there's sort of an obvious map here, right? Which is that xy maps to, well, or sorry, x mu here maps to x mu, right? Because y is just mu x. This map is x mu. Okay. That's sort of the that's sort of how you construct up C, but I can sort of do this to singulars also, and something which is kind of different, because the set of tangent directions to a singular thing will sort of look different, right, than the tangent directions to a smooth thing. If I set tangent the blow up at P of the surface S. P with so the
Sorry to interrupt. Don't know if you can hear me. The audio is gone for the people online for 2 minutes or something. We can't hear you.
Oh, I saw a little blue light.
You did? Oh.
They say it keeps it
I see. It's just finicky. Let me be careful with
I
it.
just hold it like
No, no.
Well,
Let me clip it to the outside so that it's not touching.
What about now?
Still working?
It works.
Okay. I'll be delicate. I'll be delicate. Yeah, right.
It's just terrible.
It's finicky, yes.
Thank you.
Did you already say how you make the blow up here in our singular point? Quite different from the plane.
Right. It is different, right? Like, because I mean, I didn't exactly describe what it means to replace a point with all its tangent directions. There is like both a sort of just algebrogeometric description of that in terms of rings, like, you know, you have a spec of rings for affine varieties, and then you replace this ring with some other ring. An alternative, maybe more satisfactory, or in this case, explanation is that I could also take the ambient C3 that contains this thing, and then I could blow up that point. That would replace it with a CP2. And then inside of that, I said it was an isomorphism away from this point. So I have this sort of hypersurface, but it's sort of missing this point. And then I would take its closure inside the blowup. So that would be another way to construct the blowup. Okay, so we've discussed resolution of singularities. Let's discuss smoothing of singularities. So after this discussion, you're going to think that every singularity is smoothable, but it's not true. Just because in the examples that you can easily write down, it's sort of clear that it is. So let's look at this. Let's consider this vanishing locus, x cubed plus y cubed minus c cubed equals 0. So no equals 0. It's just the vanishing locus of that in C3. So the sort of key question is, so the motivating question is, can we deform this surface until it becomes smooth? So what do I mean by deform? Well, what I mean is that in this case, for instance, it just means that we deform the equation that we started with. So we're going to introduce a variable t. So this new variable t is going to be sort of our smoothing parameter.
The audio is gone again.
No, I'll just readjust each. Yeah. Is it working again?
It's working? Yes,
Yeah?
Yeah.
Okay. So let's introduce a new is we're just going to consider the vanishing locus of x cubed plus y cubed minus. Oh, I see. It has to hold like this. This side at the bottom. All right. We'll see.
I mean, he can hold it for you.
No, I mean, it's going to be easier if I hold it myself, I think, than if you hold it. You're going to be, you know. Yeah. Is it working now? Okay. All right. Well, we'll see. Okay. So we have this projection onto the last coordinate, and inside of here, we have the point, we have 0. So this is the point where t equals 0, right? And if we look at the sort of inverse image, so like the inverse image of 0 in here will be the vanishing locus where this t is 0. And so that gives our original singular surface, right? But then, so let's say, yeah. So our surface is the fiber over 0. And now let's consider the fiber over some nearby point, which is not 0, right? So the fiber over some non-zero point will end up actually being, so it's if t is close to 0, it's going to look kind of similar, but it's not going to actually acquire this sort of singularity. So this is going to be the fiber over t not equal to 0. And in particular, this is a smooth complex surface. So this is what I mean by deforming the surface until it becomes smooth. Okay, so I have a whole family of surfaces where one fiber is my original thing, and any sort of nearby fiber is a smooth complex surface. All right, so that's the definition of a smoothing. Oops. So this really raises the question, well, like, how could something not be smoothable, right? Like, it seems like you could just deform the equation a little bit and get something smooth. Okay, but this is not so obvious because, like, maybe, my S is the vanishing locus of like 20 equations in C7, which intersect non-transversely. And the issue would be that you would have to, if you sort of just deform these 20 equations randomly, then probably the intersection of all those equations will actually be empty in C7, right? Like, a surface in C7 will have codimension 5, right? So these equations have to have a lot of coincidences to actually produce this vanishing locus, which is a whole surface. right? But it's like you would have to deform all the coincidences too to keep a surface. And this may not be possible in such a way that you actually produce a smooth surface. So there are examples of singularities that are not smoothable. Yeah, sure.
Like go to a high enough dimension and move it out there, like go to C50 or something, introduce 50 other variables, project down to C43 and over 0.
Well, the problem is that
Then you need even more equations. Right?
yeah, like the general fiber, if you deform these equations, like using parameters like this T, the general fiber is going to be like empty. So it's not really, yeah.
Not necessarily, right, but it might be.
Yeah, it might be, for instance, yeah.
It has to be like this.
Yeah. So like for a hypersurface, for the vanishing locus of one equation, it's always smoothable because you can always just deform that equation a little bit and then you get a new surface. But let me in fact give an example. So like an example would be if we let E be an elliptic curve and we embed E by a line bundle of degree at least 10. So essentially we embed E into projective space of dimension 9, and then we take the cone over this. So we have this elliptic curve, and we take the cone over it inside of C10. This singularity will actually not be smoothable. So, so this thing is the sort of affine cone. So P9 is the set of lines in C10. We just take the union of those lines and we get this cone in C10. So this would be a surface in C10 because E was a curve, and E parameterizes a family of lines. So that would give a surface. And this singularity is actually not smoothable. It's very related to this Luyanga conjecture, in fact, that example. Sorry, yeah, let's say where L is ample and the degree, I guess, well, I don't need this condition because it's automatically ample. The degree of L is 10, let's say. So this is embedding by the sections of the line bundle L. Okay. So now let me define cusp singularity. Did it stop? Good again? Okay. Okay. Singularities. So these are certain special types of surface singularities. So these are surface singularities. So let me just give the definition. These are surface singularities. Let's call it, so I'm going to call it S bar, comma, P. Okay, so this is the singular point. On S bar. So these are surface singularities S bar P, whose resolution, so remember the resolution was gotten by blowing up. And let's write it as S comma D, mapping by this pi to S bar P, is a cycle of rational curves. So cycle of rational curves, or gives a cycle. Really, sorry, I should say has exceptional divisor. Has exceptional divisor. a cycle of rational curves. Okay, so what is a cycle of rational curves? It's just, you can, like in algebraic geometry, we draw complex curves like real curves, as you've already seen. So it's just a bunch of CP1s that are sort of where you successively glue 0 and infinity of each CP1. Okay, so this is isomorphic to P1. These are all P1, and infinity of one P1 is glued to 0 of the next in the cycle. And I'm going to label these, so like D0, D1, D2, D3, 4, 5, 6, 7. Okay, great. So this D here is this exceptional divisor, which is pi inverse of P, is the sum, right? D0 plus ... plus D7. So somehow it's a singularity whose set of tangent directions is this cycle. That's all it is. Okay. And this is also an elliptic singularity because that cycle has genus 1. This is an elliptic singularity. All right. And associated to this cycle, I want to associate some sequence of numbers. So we're going to associate really a cycle of integers, di, and they're going to be defined as the negative self-intersection number of the di's. So maybe in the interest of time, I'll just sort of explain sort of in words and a very minimal picture, like what does it mean, this di squared? What it means is that I take my my curve and then I deform it slightly. So something like that. I deform it just a little bit, and then this CP1 is a surface. This slightly deformed thing is a real surface. This slightly deformed thing is a real surface. And I'm inside a four manifold, a real four manifold. And so generally they'll sort of just intersect in some finite number of points. And it's a fact from topology that these intersection numbers come with a natural sign associated to them, either a +1 or a -1. And I essentially just count up the number of pluses minus the number of minuses, and that is this number di squared. But then I took the negative of it, and we'll see why in a second. Yeah, sure.
What do you mean as an unlimited singularity? I mean, you have more than one curve.
Yeah, but the point is that the union of all of them has one loop, sort of. So it's sort of the arithmetic genus of the exceptional divisor is 1, is another way of saying it. Yeah. So the notion is singular curves by this concept of arithmetic genus, and that's what you are using here to mean elliptic. Okay. So we're going to associate the cycle of integers di, where these are the sort of so-called self-intersection numbers. And I'm just going to take it as a fact. So just a fact that if I take the intersection matrix of these di's and dj's, ranging over all I and j, right? So this is, in this case, it would be a matrix, right? Encoding all of the intersection numbers. Oh yeah, maybe I should say you don't have to take a self-intersection. You can also consider just the intersection between two curves. Well, what is this matrix? Well, it's like minus D0, and then D0 intersects D1 exactly once. So number is 1, and minus D1, 1, 1, minus D2, etc. So that's sort of this matrix. And this matrix has to be negative definite. And furthermore, these DIs do not ever equal 1. So advanced people, this is saying that this is a minimal resolution of the singularity. There's no curve of self-intersection, no smooth P1 of self-intersection -1 in the cycle. So, because otherwise you could contract it by the Castelnuovo criterion. Okay. So, yeah, sure.
How this self-intersection is verified? I can perturb it to test once and sometimes two. And
no, yeah, that's the amazing thing, is that you can't, no matter how you perturb it, if you count the number of intersections with sign, it's always the same number. Like, so here's an example. Like, let's take CP2, right? So complex projective plane, and inside it, we can take a line, CP1, a line. Well, if you're familiar with Bézou's theorem, no matter how I deform this line to some other line, there's always going to be one intersection point, because any two non-equal lines in CP2 intersect. And so the sort of self-intersection number of CP1 with itself will equal 1 in CP2. Yeah, so yeah, you can't get rid of the intersection. And the key sort of property of this, which makes you not be able to get rid of the intersection, is that this thing is compact. So you can't make an intersection point run away. To be fair, this thing may not be compact, but there's sort of a compact neighborhood of this cycle, and that's enough. All right. Are there other questions? All right, so, okay. Oh, yeah.
Point out that you might sometimes have to perturb smoothly instead of.
Yes, absolutely. So in fact, there are no holomorphic perturbations of these curves. Like, you just have to, and that's why there are minuses, possibly, also. Like, two holomorphic curves always intersect positively. But yeah, so there is, like, you're really thinking of it as like two surfaces in a four manifold. Two real surfaces in a real four manifold. Okay, so exercise for the people that, you know, are bored and don't care anymore, is that this is negative definite. This condition is negative definite if and only if di is greater than or equal to 2 for all I, and di is greater than or equal to 3 for some I. Okay, so that's the condition that this matrix is a negative definite matrix. Okay, and so in fact, cusp singularities are uniquely determined by these numbers. So the sort of set of cusp singularities is in one-to-one bijection with the set of cycles of integers, let's say d0, d1 through dn, with all of the di's greater than or equal to 2 and some di greater than or equal to 3. Of course, mod the natural sort of equivalence, which is that, like, we should be able to rotate the cycle. That just corresponds to re-indexing these components, right? And we should also be able to flip the cycle. That corresponds to changing the orientation of the loop around the cycle. Okay, so that's pretty much it. I mean, that's like a nice sort of straightforward classification of these singularities. Maybe I'll leave this.
So some very similar things happen in yesterday's talk, but don't jump into a conclusion yet. Okay, wait, it's not the same thing.
It's it's not the same thing yet. That's right. Okay, so now, so this is about mirror symmetry. So where does mirror symmetry come up in this picture? So another sort of amazing fact is that these cycles slash cusp singularities, since the cusp singularities of them as the same thing, these come in dual pairs. Okay, and I will just write down the formula. So if I say that omega is d0 minus 1 over d1 minus 1 over d2 minus 1 over ... So an infinite continued fraction like this, then 1 over omega will also have an infinite continued fraction like this. So this is going to be like d0 prime minus 1 over d1 prime minus 1 over d2 prime minus 1 over ... And by definition, the cusp singularity associated to these primes is the dual cycle. And you can clearly see that the dual of the dual is the original, because 1 over omega is omega. Okay? So yeah, that's kind of an amazing fact. Maybe another fun thing to check is that if something has an infinite periodic continued fraction, then it is a quadratic irrational. So it's the solution of some quadratic polynomial with integer coefficients. And the converse is also true. So if you have a quadratic irrational, then it has such an expansion. So because 1 over a quadratic irrational is a quadratic irrational, we get this sort of thing. Yeah, but they go in a cycle, right? So it's kind of natural to just keep going, right? You just keep going. Once you get to D7, we'll go to D0 again, D1, D2. Yeah. Okay. So yeah, so the conclusion is that we have these dual cycles D and D prime. Okay. So
What is omega?
Omega is by definition this number. Yeah. Just a real number. Yeah. Yeah.
So this point is
Yeah. Yeah, this is a definition, say. There are other ways to define it, like, yeah, it will reduce to this definition, of course, it's sort of, there's a way to use it in terms of matrices in SL2Z also. Okay, so cycles appearing on rational surfaces. So cycles on rational surfaces. So,
And you need to determine this prime di's from this just.
Yeah, because like D0 prime is the ceiling of this number, and then etc. Reciprocate, take the ceiling, reciprocate, take the ceiling. Yeah, well, except that I lied slightly, like because there's kind of a finite, there's sort of a finite like tail before it goes fully periodic. So you kind of have to ignore the finite tail. I mean, there's lots of lies in this talk. So, I mean, why should I point out this one after there have been so many? Okay, so okay, so cycles on rational surfaces. Okay, so this is sort of what relates to the previous talk. So like in the last couple talks we saw last time, we sort of saw a discussion of these Luyenda interiors. And so how did we get these Luyenda interiors? So these are sort of gotten by, I mean, well, there's the definition, which is that, you know, it's the complement of an anti-canonical cycle on a rational surface. But, you know, how are they explicitly gotten? They're gotten by blowing up toric surfaces. Yeah, gotten by blowing up toric surfaces on the toric boundary. So, you know, if you know what that is, that's great. If you don't, let's just think of a toric surface as CP2 and the toric boundary as the vanishing locus of XYZ. So maybe I'll give just a couple examples. So like examples of toric surfaces. So we could consider a complex projective space, and we can consider a set of 3 lines on it. So this would be like the, say, the vanishing locus of XYZ. So it's where the 3 lines are where X, Y, or Z equals 0. Another might be P1 cross P1. And then we consider the anti-canonical, so the toric boundary of P1 cross P1. So this is the sort of locus where the C star squared action has a lower dimensional orbit, would be the locus where one of the 2 coordinates is 0 or infinity. And so that gives a square. And I like to label, so these are sort of my pictures of say, these Luyenda pairs. And I like to label the cycle by the self-intersection numbers of the components. So like if we take a line and we take its self-intersection number, as we discussed, we got 1, because if we deform the line, it intersects itself once. And all 3 of these components, in fact, have self-intersection number 1. And similarly, with this thing, well, like if I have, there's this projection map onto either factor. And so I can clearly deform the fiber over 0 to the fiber over like 0.1. And I would get something completely disjoint from my original curve. So that self-intersection number is 0 because I can deform it to be completely disjoint, right? In fact, so all of these are 0. Okay, so that's my little picture of a toric anti-canonical pair. And so what do I mean when a sort of cycle, like as we've discussed in the rest of the talk, is on a rational surface? What I mean is that I can blow up points to get that cycle. So let me consider the following blow up. So maybe I would take the blow up at, I don't know, 3, P1, P9. Maybe I'll blow up at 9 points, P1 cross P1, with this sort of cycle of rational curves. And the points that I'm going to blow up are on the toric boundary. So I'm going to blow up like maybe 3 points on this bottom component, 2 points on the next, 2 points on the next, and then 2 points on the next. So these are P1 through P9, the 9 points that I'm blowing up. Okay, and what sort of Travis discussed was that if we make this blow up, then we get a new Luyenda interior. We get a new anti-canonical pair. So we get some sort of surface S, and we have some kind of anti-canonical cycle here. And then we have the 9, since this was smooth, when we blow up, we get a CP1, right, for each of these points. So we get 3 CP1s here, 2 CP1s here, 2 here, and 2 here. Great. So that's our new surface that we get when we blow up, right? So maybe I already wrote blow up here, so I'll say equals. Okay. And now this thing has this white cycle here, which is an anti-canonical divisor. So like there's a D0, D1, D2, D3. So we have this cycle of length 4 on S, right? And so a fact that you have to, check in the privacy of your own home, the self-intersection number of this curve decreases by 1, okay? And so D0 here, because we blew up 3 times, D0, this curve is going to have self-intersection -3. So D0 will be 3, and then D1, D2, and D3 will all be 2, because we did 2 blowups on those. Okay, so we get the cycle 3, 2, 2, 2. And this happens to be dual to the cycle 4. Okay, so this is dual. Okay. So I have an hour, right? So I have 5 minutes left. Is that right? Oh, sorry.
Maybe we can give you a second.
Sure. Okay. Yeah. Thank you. Right. I feel like I lost at least 5 minutes holding this thing. Okay. This is like the cycle D, and this is like the cycle D prime. Okay. And so since there is a Luyenda pair with this cycle 3, 2, 2, 2, we say that D is, or well, how to say, D like lives on a rational surface. Okay, this is my definition: lives on a rational surface. So concretely, what I mean is that the self-intersection sequence of D is realized by the self-intersection sequence of an anti-canonical divisor on some rational surface. Okay. Yeah. Using this formula. Yeah, I mean, there's actually a really explicit formula for it also, but it's kind of a complicated explicit formula. So this is a slicker definition. Okay, so we say then that this D lives on a rational surface. Okay, and not all D do. Okay, so not all cycles can be realized on some rational surface as the anti-canonical divisor. So maybe the simplest example, unfortunately, is like 3 followed by 10 2s. Okay, like you cannot find an anti-canonical pair whose self-intersection sequence of its cycle of rational curves is -3, -2, -2, -2, 10 times. Okay, just doesn't exist. All right, so now I can finally state Luyenga's conjecture. say lives on a rational surface, yeah, as an anti-canonical divisor. Let me put it in. So we say that that cycle, you know, whatever, it appears on a rational surface as an anti-canonical divisor.
Yeah, I mean, so you can think of it as a local area pair with maximum boundary.
Yes.
Not degenerate, maximally degenerate.
D is the maximal boundary of some log Plabbiau surface. That's the statement. Okay. And so then the theorem is Luyanga's conjecture. So this is due originally to Gross-Hackton-Kiel, and myself is that the point is that the cusp singularity associated to D prime is smoothable, which we discussed in the previous sort of sections, if and only if D lives on a rational surface. Okay, so this gives us sort of criterion for the smoothability of a cusp singularity in terms of this dual cycle. And since I do have 5 extra minutes, maybe I'll just talk about how one might go about proving this. Oh, sorry. Okay. Okay. So here's the proof. So yeah, so what do we want? Well, first of all, actually, Luyanga showed one of these directions in his paper. He showed that. Wait, shoot. Okay, yeah, he showed that that this implication holds. If this singularity is smoothable, then the cycle appears on some rational surface. Essentially, from the smoothing itself, he constructs this rational surface with the cycle on it. And so the sort of open part of the conjecture was the reverse. Okay, so the proof, which is sort of this reverse direction, is so we must start with a surface, let's say, rational surface S, with D, an anti-canonical divisor on S. So here's my sort of picture of S, and then we have our cycle D. Okay, and so we learned from the previous talk that there's always a toric model of this, right? So this can be sort of realized as a blow-up of some sort of toric pair, maybe S bar, D bar. Okay. So maybe there were some number of exceptional curves here that we blew down, and then we got this sort of toric surface. And then associated to this toric surface, we have something called a moment polygon. So we sort of discussed it with the students after the previous lecture. So I'll just assume that we know that. So take a moment polygon. For this S bar, D bar. So this is actually just some lattice polygon in the plane. And for each blow up, we're going to sort of do some kind of surgery on this moment polygon. I don't think we've discussed, have we discussed these surgeries yet? I'm sorry, yeah, I just didn't have time to get to it, but we'll maybe at some point we'll discuss these surgeries. And so there's some sort of procedure that you can do to a polygon given by cutting out certain triangles from it and then gluing the other two edges of the triangle together. So essentially you glue the two edges of a triangle together. Okay, so this matrix came up in Mark Gross's talk about the sphere. Okay, and then what you do is you reinterpret this moment polygon as a fan instead of a moment polygon. So that's sort of mirror symmetry. You take some triangulation of this moment polygon with these triangles cut out. And from it, we can produce some singular surface. By viewing each vertex as the fan of some toric surface. So built from toric surfaces. And from this singular surface, ultimately, you can prove that like this is actually, this is sort of the resolution of a smoothing of the dual cusp. So, okay, that was an excessively short summary, but the main point is that somehow, you know, we take some sort of polygon associated to this thing, and then these blow-ups of these points on the toric boundary correspond to cutting out certain triangles from these from the moment polygon. And this has an interpretation in symplectic geometry as the base of a Lagrangian torus vibration. So in some sense, this is some example of mirror symmetry. Okay. So maybe I should stop there. Yeah, since I'm way over. Yeah. All right. Yeah.
The cycle for resolution
of some other singularity. Yeah, exactly. Yeah, because these singularities are in bijection with those cycles that have that property. And yeah, like also when you take the reciprocal of a number less than 1 and take the ceiling, it's always 2 or more. So like you always get a new thing like of the same type, you know? Yeah.
What is the singularity example?
Well, this one I didn't actually, okay. Maybe wait, the example that I did before. Okay, the example I did before was like P1 cross P1. I should have just done that one. Yeah, like, so yeah, in this P1 cross P1 example, a moment polygon for P1 cross P1 is a rectangle, right? And now we're supposed to do sort of 3 surgeries on this side, 2 on this side, 2 on this side, and 2 on this side for the number of blowups. And so we sort of cut out a bunch of stuff, you know, and we sort of concretely cut out these triangles. They don't have to all be the same size, and sort of glue the 2 sides of the triangles together. And then the point is that when you sort of triangulate this thing, into a bunch of lattice triangles of area 1/2, this ends up as like a dual complex of the central fiber of a smoothing of this of the dual cusp singularity. So that was the dual of this 3, 2, 2, 2 was this nodal guy with self-intersection -4. So if we contract this to a point, then, and on some surface, then if we smooth it, then the smoothing would have a resolution whose central fiber is this object, is encoded by this object. So yeah, I mean, it's a lot of, maybe that's a lot of words. This encodes the combinatorics of a resolution of the smoothing.
So what was the initial motivation to define this? I mean, how did the Wenger come up with this definition of duality?
He didn't come up actually with came up with the definition of duality. And something I didn't mention, which is very cool, is like, I don't know if you have you heard of this like Enriquez Cadira classification of surfaces? There's like a classification of algebraic surfaces into a bunch of types. Well, it's kind of been complete because like, or if you want to consider compact complex surfaces, there are more. And it turns out that there's some sort of compact, so this is called a Hirzebruch-Inoue surface. So these are really like the people that discovered this sort of duality. There's this surface S, and it has these two cycles on it, possibly of different length, D and D prime. And the components of D prime are the only curves on S. This is a compact, complex surface S. So like people were trying to classify compact, complex surfaces, and these surfaces came up that had exactly two cycles of rational curves on them. And there was one such surface for each pair of dual cycles, essentially. So that was like originally where this duality came up. Yeah, how does the continued fraction come up? Yeah, so it comes from the construction of this surface, actually. So the point is that you take S. So S is essentially, you take C star. So first of all, when you have this omega, which is like D0 minus 1 over D1 minus 1 over whatever, this omega is equal to something like an eigenvalue of the product of the matrices 0, minus 1, 1 di. I equals 0 to the length of the cycle. Okay? So like that's the equation that you get when you figure out what this omega is, that it's an eigenvalue of this element of SL2Z. So let's call this gamma. So what you do is you take S is essentially that you take C star squared and you mod out by the action of gamma. And then you compactify it. And this compactification is by these two cycles. So it's essentially it's actually kind of coming from toric geometry, but like toric geometry of infinite type toric surfaces.
Yesterday we saw a classification of Luján pairs. Can we, I don't know, compare to these constructions or put one construction forward?
Yeah, so I mean, you use the classification of Luján pairs as like sort of blow-ups of toric surfaces at points. That's like, it gives you an algorithm, for instance, to check if the dual cycle is smoothable. Because this condition, like that D lives on a rational surface, this is kind of just explicitly checkable. You take some toric surface, And then we said we know what happens when we blow up a point. One of the numbers decreases by 1. And we know what happens when we blow up a corner too. So
I think by classification, maybe you mean the positive, negative.
Yeah.
Yeah, so here, the only relevant part of that story is the negative part.
Okay.
yes,
The
yeah.
positive part somehow is completely unrelated to this story. It's related to some other stories concerning singularity, but not this one.
And the middle.
Oh yeah, well
It's related to some other story, but again, not this one.
well, yeah, so actually the middle, the indefinite one, that's related to the singularity I wrote at the beginning, the simple elliptic singularities. It's where the resolution is a smooth elliptic curve. And yeah, so like, and right, yeah, so the point is that we said D was a negative definite cycle, right? Or that we said that matrix was negative definite. And so that was exactly this classification of the types. So this is a negative definite anti-canonical pair, or log Clebiow.
I mean, in the generation.
Oh yeah, sure. So like, yeah, I should have mentioned, like a cycle of length 1 is by definition like this. Cycle of length 2 is like this. And then beyond, it's just like polygons. Yeah. Yeah, they fit into this sort of, yeah. So for instance, like if this computation shows that this cusp singularity is smoothable.
Any question in the Zoom room? Could you ask him?
Oh, sure, yeah. Are there any questions in the Zoom room?
I have a question. So the proof of smoothability from the moment polytope by triangulations, is that in any way similar to Vero patchworking?
To what?
Vero
patchworking?
I don't know. I don't know what that is.
I think it seems it's a Vero patchworking would take some tropical curve with respect to that triangulation. So it's related to degenerating, and like this degenerates something. Vero patchworking would kind of try to build some subvariety from those pieces. So like if you draw some kind of tropical thing where they match along the ends.
You mean like if you drew some sort of tropical curve in here?
But
like
inside each of your triangles, draw something so that they match.
Like this sort of, or?
Like dual to the triangles, I suppose.
Triangulation.
Oh, in the triangulation.
Yeah. So
yeah.
Then you could build something that lives over that, a complex curve that lives over that.
Oh, sure. I see. Yeah. So the way to think about holomorphic curves in this thing is by these weighted balanced graphs that are embedded in the integral affine structure and whose leaves kind of terminate on the singularities. Like these singularities, there's some like nodal fiber of the torus vibration, and the vanishing disk of a holomorphic curve tropicalizes to like a straight line sort of coming out. I guess actually not in the Lagrangian direction. Well, whatever. Yeah.
Let's stop and thank you.